Alright, so today I want to start chapter 11, and chapter 11 is about, chapter 11 is about sequences, series, and power series. It's a long section and it's a lot of stuff in it, okay? We're also going to discuss Taylor series in that chapter. So let's first discuss with or start with sequences, something we did do in Math 1540, college algebra. So when we say a sequence, what do we mean by a sequence? A sequence is a function. It's not just any function, it's a function whose domain, so the domain is very restrictive, is a set of positive integers. So basically the domain is 1, 2, 3, 4, 5, and so on. Okay? Set of all these. So that's what makes a function a sequence, if its domain is a set of all positive integers. A sub n is called the nth term, just like we have f of x to be the function value. A sub n is an nth term of a sequence, which is the general term. It's like having f of x equal 3x plus 1 per se, so a n equal 3n plus 1. General term. Gives you all the terms that you want, where n is 1, 2, 3, and so on. And a1, a2, a3, a4 are called the terms of the sequence. This is the first term, second term, and so on. Like f of 1 in functions, f of 2, f of 3, f of 4, and so on. For example, if I'm given a sub n, the nth term or the general term of a sequence to be n over n minus 1 factorial. This means factorial if you forgot what that is. So to find the first term, you put in a 1 for n, and then you get 1 over 0 factorial, 1 over 1, which is 1. To find the second term, a2 is 2 over 1 factorial, 2 over 1. To find the third term, a3 is 3 over 2 factorial, 3 over 2, 3 over 2, and so on. a4 is 4 over 3 factorial, 4 over 6, 2/3. Also, just to remind you what a factorial means, it's if you want to find, say, n factorial, you start with n, times it by the one, by the one next, the one below it, and then the one below it until you reach 1. Like 5 factorial, you start with 5, and then 1 less, 1 less, 1 less until you reach 1, and you times them together. And your calculator actually has that key if you don't know. So say you want to do 6 factorial, so you go 6, and you go to math, and you go to PROB, probability, and you can see number 4 is like exclamation mark, so 6 factorial. The calculator did 6 times 5 times 4 times 3 times 2 times 1, and it got 720. Okay. So you can find all the terms of the sequence given its general or nth term. Now the question is, how do we come up with this general term? It's sometimes it's easy, other times it's kind of tricky. So to find the general term, you always want to look for a pattern, and usually you want to look, you want to look between, you want to try to find a correlation between the terms and their indices, like a1 with 1, a2 with 2, and so on. So for example, how do we find the nth term or the general term of the sequence? So it's easy going this way. Now what if I'm given the terms? How do I find the general term? So say I have 1, negative 1 over 4, 1 over 9, negative 1 over 16. Of course, they're not going to give us all the term, but they'll give us enough to figure it out. So you can see just some observation that like this is negative 1 over 2 square. This is 1 over 3 square. This is negative 1 over 4 square. I'm trying to find a pattern. And 1 is obviously 1 over 1 square. So at the bottom, so this is A1, A2, A3, A4, and so on. So we want to find AN. So it looks like AN is going to have at the bottom like 1 square, 2 square, 3 square, so it's going to have N square. And on top, it's going to have 1, right? But it's not always going to be a 1. It's a 1 and negative 1. So when your terms alternate, plus minus, or minus plus, then you're going to have either negative 1 to the n or negative 1 to the n plus 1. You have to test it. What do I mean by test it? Put the value of n. When n is 1, negative 1 to the 1, your first term is negative, which is not the case. So you have to put plus 1. When n is 1, negative 1 squared is 1, so you know it's going to work. Okay? So it's either, so when your terms alternate, either this or that. And then test it to see whether your term is positive or negative by plugging in n equals 1. Here's another example. 1 plus 1 over 2, 1 plus 3 over 4, 1 plus 7 over 8, 1 plus 15 over 16, 1 plus 31 over 32, and let's find a pattern here. So again, this is A1, A2, A3, A4, A5, and we want to find the nth or the general term. Okay, so it looks like every term has a 1, so AN is going to have a 1 plus. Now you have 1/2, 3/4, 7/8. So it looks like you have 1 and 1, 3 and 2, 7 and 3. So 1 and 1, it's 2 minus 1 basically. And this is 2 squared minus 1. To get 3, I'm trying to find a link between this and that. And this looks like t cubed, 2 cubed minus 1, which is 3. 2 to the 4 minus 1. So you're going to have 2 to the n minus 1 over. Here at the bottom, as you can see, it's 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, it's 2 to the n. This wasn't as easy, but you just have to practice those, okay? So we define the sequence, the limit of a sequence using epsilon delta from Calc 1. So definition of intuitive limit of a sequence. So let L be a real number. The limit of a sequence AN is L, which we know how to write this limit of AN as n goes to infinity is L if for every, we call this for every or for all epsilon positive, there is a real number m positive such that the difference between AN and L is less than epsilon whenever n is greater than m. We use this to prove stuff. So basically, if I have anything to use this on the test, it will be extra credit. So what we need to know from there is sequence that have limits. So if the limit exists, that means they converge. And if the limit does not exist, then the sequence diverges. That's very important. So because that's going to help us decide whether a sequence converges or diverges. We find its limit. If you get a number, then it converges. If you get, say, infinity or two different numbers, depending on which way you go, infinity, negative infinity, positive infinity, then it diverges. And okay, like I said, this I will not ask about unless it's extra credit, but you need to know this will test for convergence. Limit and if you get a number, then it converges. If you get say infinity, then it diverges. Okay. Now let's look at another definition of limit. Here, let L be a real number. Let L be a real number. Let F be a function. This second theorem is for evaluating limit of a sequence using function, using corresponding function. Be a function of a real variable such that the limit as x goes to infinity f of x equals L. If an is a sequence such that f of n equal an. So for example, if f of x equals 2x plus 1, that means an is going to be 2 plus 1. So it's a matching sequence, okay? Then the limit of an as n goes to infinity is that. So basically, what this is telling us, if I want to find the limit of a sequence, it's like finding the limit of a function. In the case of a function, x goes to infinity. In the case of a sequence, n goes to infinity, and they will give you the same result. Okay? So, for example, how do we find the limit as n goes to infinity of an, where an is cube root of n over cube root of n plus 1. Now we can use f of x here, but we don't have to. But I'm going to show you that you could say limit as x goes to infinity. Instead of n, we could do cube of x, cube root of x plus 1, which would be infinity over infinity. We use L'Hopital's rule. So this is going to equal limit as x goes to infinity. The derivative of x to the 1/3 is 1/3 x to the negative 2/3. And that's also 1/3 x to the negative 2/3, which is 1. And the limit of 1 is 1. So the limit as n goes to infinity, cube root of n. We could just do it with this and do L'Hopital's rule assuming n the variable. Okay, you don't have to do x and then go back to n. I'm going to show you the next one. So how do we find the limit as n goes to infinity of n minus 2 factorial over n factorial? Now, you know, we can actually reduce this. Just to give you an idea, like say you have 4 factorial over 6 factorial. How do you reduce this without calculating it? Like 4 factorial is 4 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which is 6 times 5 times 4 factorial. So you can reduce that and you end up with 1 over 30 as your answer. So we're going to follow the same strategy here. N minus 2 factorial over n factorial. N is n minus 1, then times n minus 2 factorial, just like 6 times 5 times 4 factorial. That cancels that out. So the limit as n goes to infinity of n minus 2 factorial over n factorial is the same thing as the limit as n goes to infinity of 1 over n minus 1, which is 1 over infinity, which is 0. And I'm sure you noticed that I didn't even go back to f of x. You don't have to. Okay, just going back to f of x just to familiarize ourselves with n. Once we're familiar with n, we don't have to go back to f of x. Now the limit laws for sequences that we will be using throughout this chapter. So if you have two sequences, an and bn, so an and bn are sequences and they're convergent sequences, and c being a constant, then So if we're doing the limit as n goes to infinity of an plus bn, we can split it up. As we know, with limit, we can do that. Plus limit as n goes to infinity bn. And same thing with minus, okay? And if you have a constant, times a sequence and you want to limit, you can pull the constant out. I think this is common sense. We've done this with limits of functions before. And if we, just like f of x and g of x, an times bn, if you're doing the limit, you can do them individually and then times the answers. Times the limit of bn and then go. Same thing with the quotient, except when you divide, you don't want to divide by 0, okay? So you do the limit of an over the limit of bn as long as the limit of bn does not equal 0. Alright, and we're going to be doing this throughout this chapter. So find the limit as n goes to infinity of 2 over n squared plus n minus 2. So we do the limit of 2, which is 2, over the limit of that, which is infinity, which is 0. That's, we always do that. So. Now we can use what we call the squeeze or sandwich theorem to evaluate limits. The squeeze, or what we call sandwich theorem, to evaluate limit for sequences, to evaluate limits of sequences. So if the limit as n goes to infinity of an is L, and the limit of another sequence bn is also L, same answer, okay, same answer. And if another sequence is squeezed between an, bn for all n greater than capital N, which is integer n, then the limit as n goes to infinity of Cn is also L. Because if an goes to L and bn goes to L, then Cn must go to L. If that means Cn, or the limit of Cn, is greater or equal to L and less or equal to L, so it must be L. So here's an example. Use the squeeze theorem. Use the squeeze theorem to find the limit as n goes to infinity of an, where an is cosine pi n over n squared. Well, we all know that cosine or sine are between -1 and 1. Since n squared is positive, we can divide by n squared and nothing is going to change. We know that as n goes to infinity, -1 over n squared to 0, this is going to 0, so this must be going to 0 by the squeeze theorem. Okay. Next, we're going to talk about the absolute value theorem. This is usually used with alternating sequences like plus minus, and so on. If you do the limit of absolute value of an as n goes to infinity and you get 0, then the limit as n goes to infinity of an is also 0. Why is that? Because an is between negative absolute value of an and positive absolute value of n. If that goes to 0, then that goes to 0, that goes to 0, and that must go to 0. Okay, very simple. Here's an example. Evaluate the limit as n goes to infinity of -1 and +1 plus 2. So this is an. If I do absolute value, because this is going to be, when n is 1, it's plus, when n is minus, or is 2, is minus, so it's going to be plus minus. So to avoid that, we do that. That's going to be 1 over n squared plus 2. If you do the limit and n goes to infinity, you get 0, so that means the limit as n goes to infinity of an is also. Okay. So now we're going to discuss monotone sequences and then bounded sequence, and then we're going to result about monotonic and bounded sequences in terms of convergence. Okay, so let's first talk about monotonic sequences. A sequence AN is monotonic if its terms are non-decreasing, which means increasing or staying the same, like A1 is less or equal to A2 is less or equal to A3 less or equal to AN, and then so on. This would be monotonic increasing, because you can see as you go from left to right, your sequences are increasing. Or if its terms are non-increasing, which means decreasing or staying the same, that means A1 is greater or equal to A2 is greater or equal to A3 is greater or equal to A4. In this case, we say monotonic decreasing. As we go from left to right, they're getting smaller. So for example, the sequence 4, 6, 8, 10, it's increasing, monotonic increasing. 1, 1/2, 1/4, 1/8, 1/16, it's monotonic decreasing. And -1, 1/2, -1/3, 1/4, -1/5, it's not monotonic, because it increases, decreases, increases, decreases, so there's no pattern. Okay, so there are, I put that in a nice handout for you. How do we determine if our sequence is monotonic? A function f of x such that f of x equals an. So if you're using a function, you find its derivative. If the first derivative is positive, as we know from calc, the function is increasing, so the sequence is increasing. If the first derivative is negative, the function is decreasing, sequence is decreasing. That's straight from calc 1. Okay, or you could do the ratio of the sequences, an plus 1 over an. If it's greater than 1, that means an plus 1 is greater than an, so the sequence is increasing. If it's less than 1, that means an plus 1 is less than an, that means it's decreasing. And or you can do the difference. If the difference is greater than 0 between the next one and the current, then increasing. If it's less than 0, then it's decreasing. So 3 ways depending on the problem. Okay, we don't know which one is easy. Sometimes one is easy, the other isn't. So show that the sequence n over e to the n is monotonic decrease. Tonic decrease. Remember, when we talk about sequence, n is 1 and above, right? Positive integer. So if we want to use, we can do this in a couple of ways. If we want to use a function, remember in a function it's all real numbers, but here it's only greater than 1, so we can only do that, greater or equal to 1. Okay, so we can find its derivative. We know how to find derivative. So g f prime minus f g prime over g square, which would be e to the x, 1 minus x over e to the 2x, which would be 1 minus x over e to the x. This would be positive. No, it would be negative if x, because that's always positive. So it's negative if the top is negative, if 1 minus x is less than 0. So if x is greater than 1, and which is the domain, n is greater than 1. So the first derivative is negative on the domain. That means the sequence is decreasing on its domain. Okay, so it's decreasing. Another way, which I did by doing the ratio of an plus 1 over an. If it's less than 1, then it's decreasing, and I'm going to show you it's less than 1. So an plus 1 would be n plus 1 over en plus 1. divided by an, which means times en over n, times by the reciprocal, and that would be n plus 1 over ne. If we cancel this with that, we get e, and that's going to be n over ne plus 1 over ne, which would be 1 over e plus 1 over ne. 1 over e is the same as 1 over e. These are equal. This is less than 1 over e, like 1 over ne is less than or equal to 1 over e, because ne is greater or equal to e. Okay, so 2 over e, which is less than 1. So we got this less than 1, and it's monotonic decreasing. Now we're going to talk about bounded sequences. Bounded sequences. A sequence an is bounded above. So we're going to talk about bounded above, bounded below, and then bounded. If there is a real number m such that an is less or equal to m for all n. So basically, all the terms of the sequence have to be less than or equal to that number so that the sequence is bounded above. Okay, so it's like an upper limit for it, okay, or upper bound. For example, well, m is called upper bound for the sequence, upper bound for a. For example, sine an equals sine of n. This sequence is less or equal to 1 for all n. That means sequence sine n is bounded above, and the upper bound for that sequence is 1. Okay, and a sequence an is bounded below. So I don't want to write this down, it's in notes. It would be bounded below if there's a real number. I'm going to use n instead of m, such that n is less or equal to an. Okay, so every term of the sequence has to be greater or equal to n, right? Every term has to be greater or equal to n, and n is called the lower bound of the sequence. Okay, saying for sine n, sine of n is greater or equal to -1 for all n. That means the sequence sine of n is bounded below by -1. -1 is called the lower bound for that sequence. And we have bounded above, bounded below, and then we have bounded. What makes a sequence bounded? If it's bounded above and bounded below. So bounded if bounded above and bounded below. That's what makes a sequence bounded. Again, sine of n, that sequence is bounded because it's bounded above by 1 and bounded below by -1. So now we know monotonic and bounded. Now we can talk about what happens if a sequence is bounded and monotonic. It's convergent. So bounded and monotonic sequences. If a sequence an is bounded and monotonic, then it converges. So basically it's bound increasing when it's convergent. Okay, so bounded above and increasing converges, bounded below and decreases, it also converges. Okay, also converges. Now, if you look at the remark in the note on page 12, it says every convergent sequence is bounded. So if you know a sequence is convergent, then it's bounded. But the converse is not necessarily true. Okay. Come on, don't pause, please. Please, please, please. Please don't do that. Froze. Why?